Thank you very much. Thank you for the invitation. So, as you said, if you have any questions, please feel free to interrupt. I don't see anything, any questions on the chat or something like this. So, I would like to talk about some generalization of Seshadri constants with some connections to combinatorics or geometry of numbers. And this is based on joint work with Atsushi Ito, and it's a paper which appeared in Advances of Mathematics in 2020. Okay, so let's start. So the aim of the talk, to be more precise now, is to first of all estimate up to bounded constants, Seshadri constants on toric varieties. This is a statement in algebraic geometry, but we have an application in geometry of numbers, which is a generalization of Khinchin's flatness theorem. And the second aim is to extend this Seshadri constants to a whole sequence of invariances, like a flag of invariance. The first and the last one are known. The first one is the Seshadri constant. The last one is also used, but it doesn't have a name. Some people use it, but not with the same name. For example, it's called the width of L. For example, appears in the K-stability when you integrate, when you have these formulas for the algebraic version of K-stability. This width at the point appear, and then we can prove using this new invariance, we can show that the volume of the line bundle is pretty much equivalent to the product of this invariance. This is an analog of a theorem from geometry of numbers, the second main theorem of Minkowski. And also we show that in the classical, in the toric case, these invariants are pretty much compatible with those defining combinatorics. So what the basic idea of this talk is to build some dictionary between algebraic geometry and geometry of numbers, and then we may think of toric geometry as being the intersection of these two domains, and then the first aim is just to apply algebraic geometry to geometry of numbers, and then the second step is to go back using some ideas from combinatorics. We get new results in algebraic geometry. Okay, so let's start. So also this is the outline of the talk. So first of all, I will recall statements which maybe you know, but please bear with me. The first from the geometry of numbers, I will just recall Minkowski's theorems, transference, what is the flatness theorem. Then we go on to this to adjoint linear systems, Seshadri constants. Then we estimate Seshadri constants on toric varieties and define and study a bit successive minima of line bundles, and finally some questions and problems. Okay, so let's get started. Geometry of numbers. The subject concerns a lattice, let's say of dimension D, and a convex body, which means that it's a convex subset, which is compact and the same dimension. In particular, it has a non-empty interior. And classically, people studied bodies which are symmetric about the origin. Yes, so a point belongs to the convex body if and only if its opposite belongs to it too. And you may see, for example, a picture, a drawing here. And the first theorem of Minkowski is concerned with the existence of non-zero. So the main question, the main question we're interested about these bodies is if they contain lattice points which are non-zero, if they have one or two, linear independent, or we can find a basis and so on. And the first theorem of Minkowski says that if there is no other lattice point besides the origin, then the volume is bounded above. And there is an explicit bound which is also sharp. It's attained by the unit cube. And you can reformulate this theorem in terms of the so-called successive minima, which were also introduced by Minkowski, of the lattice and the convex body. The first one, the first successive minima, is the smallest enlargement of the body, which contains a non-zero lattice point, and the ith successive minima is the smallest enlargement, such that you have at least I linearly independent lattice points, and you get a sequence of invariants which are called the successive minima of the lattice and the body. And you can reformulate the first theorem of Minkowski as saying that you have this inequality. So if the volume is well, you can just see this inequality. If the volume goes to infinity, then lambda 1 must be approaching 0 in particular. And the second theorem of Minkowski says that you can actually control the volume using this invariance. So up to constants, the volume is the same as the 1 over the product of this invariance. Again, inequalities are sharp. And then the next result I want to mention from geometry of numbers is the transference theorem. And then for this, let me recall that if you have a lattice, you can take the dual, and you have a duality pairing, natural duality pairing, which extends to the reals. And given a, let's say, zero symmetric, in our case, convex body in lambda r, you can compute the dual body, the polar dual body, which is defined this way. It's a bit, it's not clear what it is, but on the picture you will see that it has a geometric meaning, in fact. For example, if we take in dimension 1, if we take the polytope consisting of, the interval minus a, if we take the dual, if we take the dual polytope, will just be minus 1 over a, 1 over a. So there is a duality here in the sense that if one is big, the other one is small. Yes, this is the principle somehow. And also the shape changes. For example, in dimension 2, if you take this polytope on the right-hand side, its dual, well, up to a change of basis is the same, but it looks different. And also, if you stretch it from one side, it will become smaller on the other side. But what we should remember from this duality, from this definition of polar bodies, is that you have if one is big, the other one is small. And then transference theorem, the transference theorem of Mahler a long time ago, and then Banachik proved a stronger, a better inequality. Is an explicit. Sorry, there's a question.
No, nothing yet.
No? Okay. I thought there was some sound. So the transference theorem basically makes this precise, this duality principle that the successive minima of one body are inverse proportional to the successive minima of the dual body. Mahler proved instead of d, he proved something like this, d factorial square, something like this, and then the proof just follows from the second theorem of Minkowski. And Banaszczyk proved this much better bound d. Even this can be improved, but anyway, it's pretty much it's good enough. And there are many applications of these three theorems that I mentioned. And for example, in number theory, you can estimate the class number of a finite field extension of a number field, or you can apply to Diophantine approximation. And then how to compute this successive minima. You can compute them. If you have a polytope, you can really compute them. And what you do is to first compute a distance function. If you have any point in the space, you can connect the origin with this point, and then see where you hit the boundary of the convex body. And this will be denoted by lambda over f of lambda, and you compute f of lambda as being the infimum of t, such that lambda is in f of t. And this defines a distance function which satisfies this property. So it's symmetric about the origin. This is the same as saying that the body is zero symmetric. The positive constants come out from the function, and then it satisfies this convexity property. Conversely, you can recover the body as the unit pole. I mean, points of distance at most one to the, according to this function. And you can compute the first minima of the lattice with respect to this body to be the minimum of this distance function for the entire lattice points which are non-zero. So this is actually the definition of the first minima, is the smallest distance of a non-zero lattice point. I should mention that the second main theorem of Minkowski was extended by Davenport and Esterman to any convex body. And so it implies the original statement, and then the statement, you see, it involves the volume of the original body, but the successive minima of the difference. This difference consists of the differences between the points of delta, and it's zero symmetric. We will actually need this generalization. This will be generalized to algebraic geometry, not the original one, because the bodies coming out from algebraic geometry are not usually symmetric about the origin. Okay, so if there aren't any questions, I move on to the next case when you have bodies which are not symmetric about the origin. And as I said, we are mainly interested in these. And the naive question, a naive question would be, can you classify the pairs consisting of lattices and convex bodies which do not contain any interior lattice points? And we can do something in dimension 1 and 2, but let's see what is the answer in dimension 1. In dimension 1, one can show that there is a lattice translation of the body, which is contained in the interval 0, 1. And this is if and only if. So we have a complete classification. In particular, the length of the body is at most 1. It's bounded above. In dimension 2, we can also give a complete answer. One can show that up to translating by a lattice point the body and also enlarging it. Basically, we slide out the faces as much as we can until we still have no interior lattice points. These maximal shapes are of three types, but which may deform. So the first type is when this maximal body is this how to say this slice x being between 0 and 1. The second one is when you have a rectangle which has the unit square inscribed, and this rectangle, you see, it's also containing this unit how to say well, so it's containing between 0, x can be at most between 0 and 1, and y between 0 and 1. In particular, this also implies that you can also see immediately that it has no interior lattice points because of these stripes, yes? Or there is the possibility that it's a triangle with the unit triangle inscribed and also containing this stripes. So we see that the volume may become unbounded in this case. If you have no interior lattice points, the volume can be infinitely large. However, there is a projection. There is a lattice projection of length at the most a bounded length, and then it was proved by Hurkens that the sharp bound is this 1 plus 2 over square root of 3, which is attained by the triangle. In the second case, you get 2. For example, in this case, in the first case is 1. Yes, you just project onto the x-axis, and in the second and third case, you just take the usual coordinates x, y, and here x, y, or x plus y. So in dimension 3, I'm not sure. Maybe some of you know the answer, but I don't see any classification at the moment. So the flatness theorem of Khinchin is that this phenomenon happens in general. If you have a body with no interior lattice points, then there exists some projection with length bounded above by a constant which depends only on the dimension. And we can reformulate this flatness theorem in terms of the successive minima. If we take the difference body and we take the dual of that, it turns out that these are exactly the functions, the linear functions, such that the length of the projection of the body is at most 1. And then the first successive minima of this body is exactly the minimal length, which is called the width, the lattice width of the body. And you can just reformulate flatness theorem as saying that if there are no interior lattice points, then the width is at most a bounded constant. And this constant has improved dramatically over the years. Originally, Khinchin proved something like de factorial. Much later, in '83, Lenstra extended to this exponential bound. And then Kanan and Lovac in '88 improved it to a quadratic one, and a bit later, Banashik improving even more. It's expected that it's linear indeed. And moreover, what is interesting, Kanan and Lovac show that if the width is large enough, then there are also lots of interior lattice points. This follows from this inequality that you see here. So, okay. Okay, and then what are some of the applications of this statement? So first of all is the integer linear programming method. the question is if you have if there exists an interior lattice point in a given body, and the flatness theorem just gives you a way to do this. But basically, you know that there is a direction for which the projection is bounded. If the projection is bounded, it contains only finitely many lattice points. Yes, it's an interval. So then you consider those slices. You have at most C of D of those. And if there are any lattice points, they should be on those slices. So basically, you reduced the dimension of the problem. From a problem in dimension D, you have a bounded number of problems in smaller dimension. So this is somehow the principle. And another application is that this flatness theorem appears in the solution in the solutions in Toric case of some open problems in the birational classification of algebraic varieties. And this was actually my original motivation. And so that's why it was natural to ask why, I mean, if this flatness theorem says something new in algebraic geometry, since being valid for polytopes is valid for toric varieties, is it true for in algebraic geometry it has a form which is valid for non-toric varieties? So the answer turns out to be yes, but there is even a stronger statement which is no. And how to do this? Basically, we just use the algebraic geometric interpretation of interior lattice points. If you have a pair, a lattice and a polytope, let's say Q polytope, so the vertices are rational. Some multiples belong to the lattice, some integer multiple belongs to the lattice. Then you can associate a toric projective variety with a natural Q polarization. And this may have singularity. So you just take any resolution and you pull back this Q line bundle. And then it turns out that the interior lattice points of the original body correspond to a basis, an equivariant basis of this adjoint line bundle. Well, sort of with this roundouts, but if everything was if it was a Z polytope, it's an adjoint line bundle. Okay, so this is it with the geometry of numbers. If you have any questions, please feel free to ask. I move on to the next section about the joint linear systems and the Seshadri constant. So we consider a pair formed by a smooth projective variety and ample line bundle. And the basic question, and please think of them as being similar to the ones asked before with empty polytopes and so on, is when this linear system K plus L is non-empty. This K plus something ample is usually called a joint linear system. If it's not empty, it defines a morphism, and then you can take the image in the projective space, and you may ask if the dimension is at least some number, or if this map is birational, and so on, or if it's a closed embedding. And the idea is that if this is false, if the answer to the question is no, then there should be some kind of special cycles which explain this. And one famous conjecture of Fujita says that if n is at least d plus 1, this linear system K plus NL is base point 3, and then as soon as it's at least d plus 2 is very ample. And Demailly realized that one can solve Fujita conjecture if one can construct in any given point a certain metric, singular Hermitian metric, which has an isolated singularity at the point, so it's smooth in a puncture neighborhood, but it should have large Lelong number at X. And then just to state this algebra, just to state the algebraic version of this, I will state this example theorem. So let's say you have finitely many points in X, x1, xa, and then you pick numbers, exponents there, and you assume that in the linear system QL you can find you can separate the points. So in other words, you can cut the points, set theoretically, not scheme theoretically. And in this, if this is the case, then you can show that that the sections of the linear system generates the jets of the given order. You can see them there at each point simultaneously. I should say that this JXL just denotes the jets of order L at the point. And the proof. The proof is very simple. You just take a basis of this vector space, of the space of global sections, and this basis if you take this basis defines a map to the projective, a rational map to the projective space, and you take the pullback of the Fubini study, and this will be a positive singular Hermitian metric, which is exactly what you want, and which has isolated singularity at each of the given points, and then the Lelong numbers are at least pi over q, and then you just apply Nadel vanishing to get the surjectivity. So, for example, if you look at 2 points, and let's say QL embeds X in the projective space, then you look at the polynomials of degree Q. Okay, sorry, I mean of the given degree there, such that they vanish of order P1 at X1 and order P2 at X2. When you ask for this, you may have some other excessive vanishing. And what you want in this example theorem of Desmailly is that this excess happens away from those points. Yes? So you may have some unassigned base locus, but not passing through X1. So in this case, we can solve Fujita conjecture. So using this idea, Desmailly was formulated this, defined this notion of Seshadri constant at of this pair at a point, and there are several definitions. These 3, for example, let's discuss them. First of all, if you take sufficiently large multiples of the line bundle, you look at the largest order of jets at X that you can generate, and you take the limit of the ratio between this maximal order of generation and n. It turns out that the limit exists, and it's denoted epsilon of Lx. It's called the Seshadri constant at X. One can also, the second definition is mostly used for computations. You take the blow up of the point, and then the Seshadri constant is exactly the supremum after all t, such that the pullback of L minus t is ample. Or you can compute it in terms of the curves passing through X. This is the same thing. And there is a third definition, which is similar, which is inspired by the example theorem, but I'm sure I saw it in a paper by Eckel, that this Sashari constant is the supreme after all P and Q, such that you can find in the linear system QP, you can find D elements which vanish of order at least P, and they cut out the point X. Or this is equivalent to this base locus being equal to X near X. In other words, there is no excess vanishing through X, through some subvariety of bigger dimension than 0 through X. And then we can reformulate the example theorem of Desmailly in the case of a 1 point, saying that if you have, saying that that this linear system K plus L generates jets of that order, that round up, So, for example, if you want to apply for base point freeness and so on, you need to find lower bounds for the Seshadri constant. So this turned out to be a very interesting problem, but not that easy. So let's see what can we say in general about this Seshadri constant. First of all, if you vary the point, then it takes this constant takes a maximal value at the very general point. So this means on the complement of a countable union of closed subsets. And this maximal value is called the maximal Seshadri constant. You have this natural property like powers come outside and also convexity. You can compute, for example, on the projective space, these Seshadri constants are all 1. Also on a smooth curve, the Seshadri constant are also constant equal to the degree. But in general, it's quite hard to compute this Seshadri constant. In the Toric case, Rocco found a formula for computing this Seshadri constant at invariant points. So if you have an invariant point, then the Seshadri constant is just the minimal length of an invariant curve passing through a minimal degree, sorry, of an invariant curve passing through the point. And intuitively, you can think of this as this is your, let's say, in the picture you have this polytope with the origin, and then you take the line x1 plus x2 greater or equal than 2, then t, and then with t small but positive, you start increasing it. As you start increasing it, the shape changes until a certain sorry, the polytope changes, but the shape does not change. And epsilon is the last time where the shape is the same. Yes. Because if you move beyond that, then you see that the first edge, I mean, the vertical edge disappears. Now, there is a general inequality, which is just obtained by counting jets, saying that the Seshadri constant is at most the d squared of the volume. And there is some very interesting question of Nakamae and Huang Keum saying that if the ratio, if these guys are not proportional, so in other words, if this ratio is somehow going to 0, there should be some explanation for this, and moreover that this Seshadri constant should come from smaller dimension. This is true in dimension 2, proved by Nakamae, and Huang and Keum have similar they have some statements in certain cases. Okay, so how about dimension 2? In dimension 2, Ein and Lazarsfeld show that at the generic point, the Seshadri constant of a line bundle is at least 1, ample. But there are examples of Miranda which shows that in special points, this Seshadri constants may go arbitrarily close to 0. So this somehow shows that it's impossible to follow the original idea of Demai to prove Fujita conjecture using this invariance, at least at special points. But in general points, it seems to be okay. Why? Because you have these bounds given by Ein, Kuchle and Lazarsfeld. So you have a lower bound saying that if the volume of the line bundle against all the cycles of X is bounded away from 0, then also this epsilon is bounded away from 0. You have an effective bound, and then the conjecture of them is that one can replace 1 over d by 1. So now, since special points are somehow harder to handle, let's just concentrate on very general points. And this is a theorem of Desmailly and Ein-Küchle-Lazar's-Feld, saying that if you have a smooth projective variety and an F MBQ line bundle, if you look at the general point, then you can generate those jets. I mean, this is exactly as the original statement of Desmailly. In particular, you have a lower bound for the dimension in terms of the Seshadri, of the maximal Seshadri constant. And then as soon as epsilon grows, you have sections, the image has dimension D, and it's even birational, yes? The proof is just Kawamata vanishing on a blow-up of X, or a blow-up of 2 points. So it's just like Desmailly, it's very easy. What I said before, so Miranda's example shows that we should concentrate on very general points. In special points, we might not be able to say much. But let me say that if you recall, we also, by Kanan and Lovács, we have Kanan and Lovács inequality says that if the width is large enough, then there are lots of interior lattice points. If you look at the inequality in 1, you also see that if the Seshadri constant is large enough, then you have lots of sections in this line bundle. So actually, this will be explained. It's actually the same thing. And I will move on to the next section if there are no questions. So what about Seshadri constants on toric varieties? And let's consider toric variety, a polarization, and then we look at the Seshadri constants at all points. First of all, due to the torus action, these numbers, I mean, these invariants are constant on orbits. If X is invariant, we know the formula by Rocco. So, and also there is a formula for all X just in terms of the invariant points and general points. This is due to Ito. So it remains to deal with the general point on a toric variety. And this is the first result with Atsushi Ito, saying that we can estimate this Seshadri constant up to bounded constants. So up to bounded constants is the same as the width of the polytope, of the moment polytope. In particular, we get a purely combinatorial statement saying that if you have a convex body of given width, if the width is at least d squared, then you have at least one lattice points. This improves Kanan and Lovács because they had some C universal, which they cannot get their hands on. Then the next statement is that if W is at least d squared plus 2, then you have the lattice points, the convex hull of the lattice points has dimension d. This is a new statement. It's a generalization of the Flatness Theorem, but it was also observed by Verkov, Hofshire, and Neal with slightly different bounds. And also, for example, you can generate a lattice if you increase the W just a bit. And then the last statements are similar to the Kanan and Lovács. So this color is just a simple application of the Theorem One and Desmailly and Ein-Küchle-Lazar's theorem. And then how about the proof of Theorem One? So there are two inequalities. So first of all, let's concentrate on the first one. So we have to show that the Seshadri constant is at most the width. How to compute the width? We just take a non-zero lattice point. We consider the image. We pick a point in the image, and we consider the slice. Let's denote by square t. Then this inclusion of the slice in the body induces a vibration which is also in terms of line bundles, in the sense that the pullback of the line bundle on the right-hand side is not contained, but I would say some section, some effective divisor plus the pullback of the right-hand side is contained in the left-hand side. And moreover, the general fiber of this vibration is P1 O of L, where L is the length of the vibration. It may not be an integer, but it's okay. So, and then by now, since you have a cycle in X, a general cycle, the Seshadri constant, when you restrict to a subvariety, can only go up. So this is the inequality, and then when you take the minimum, you get the inequality. So this is quite easy. The second inequality is a bit more difficult. One uses Transference Theorem. So one knows by the Transference Theorem that W is at most D over the lambda D of the difference body. So it's enough to show the stronger inequality that epsilon is at least that. And then we can do this just by using the definition. So this means that we have some linear independent elements such that I mean, we have linear independent chords through the body, such that their length is at least 1 over the lambda d. These chords define again rational morphisms, rational vibrations dominant to P1 and O of 1. So in particular, we can find some. If you look at the section through 1, the general section. You can, this will be a toric passing through the origin, and it's actually you can compute it. And because of the linear independence of these elements, when you intersect them, you get a point, you get 1. So in particular, by the definition of by the third definition of Seshadri constants, it's at most epsilon. Okay, so now I move on to the next chapter about the successive minima of line bundles. So you see in the previous proof, we show that the maximal Seshadri constant is almost the same as 1 over the last successive minima of the difference body. And the proof involves the different successive minima, lambda 1 star and lambda d. So the question is, do these lambda have algebraic geometry meaning? And the answer is yes. And we can define them like this. So we take a proper algebraic variety, irreducible and irreduced, may not be normal. And we take a line bundle on it, we fix a point, we fix a t, the real number, and we consider this a bit ugly looking notation, saying that we look at all those sections which asymptotically vanish of order at least t, strictly. Yes. This is a closed subset, Zariski closed subset. It's increasing with respect to t, and clearly if t is large enough, then it's the whole space. Yes. And one consider the place where the codimension of this space is jump. Yes, jump near x. So you may think of these spaces as being some kind of failure of postulation loci. And you get a sequence. So unlike the successive minima in convex geometry, these guys are decreasing. You get them decreasing, and they end up the last. They can only go up to d, to the dimension. And one can show that they are constant if x is very general. The constant value is called is denoted epsilon I of L. And one can show that if the Kodaira dimension is at most 0, then this epsilon 1 is 0. And if the Kodaira dimension is at least 1, then it's detected by this sequence. So in other words, epsilon of the Kodaira dimension is the last one, which is strictly positive. And if L is big, then this is an invariant. This is a numerical invariant. This epsilon I. So the maximal value, not at any point. If L is semi-ample and X is smooth, then it coincides with the Seshadri constant of the MIE. In particular, if L is semi-ample, then epsilon D coincides with the maximal Seshadri constant. What is the first successive minima? Just by definition, is the largest order of vanishing, asymptotic order of vanishing that you can impose at a given point with all the sections of L. We call it the width of L at X, and there is an inequality saying that the volume normalized by the multiplicity of the point is at most the first one and at least the last one. This is the right-hand side inequality, which is just an analog of the first mirror, the theorem of Minkowski. Is just jet counting, and then the left-hand side is just some local multiplicity computations. In particular, if you have an irreducible curve but with some singularity and L is positive, then you have a formula for this first and actually the last in this case successive minima is the degree over the multiplicity. What happens now when we vary the t? We fix x and L and we vary t. So what happens is that this successive minima break the whole positive reals into certain intervals where the loci have they're not the same, but somehow the codimension is the same. So for example, if dimension is 1, if t is strictly larger than epsilon 1, this base loci is x, and then if you go just beneath it, it's your point. So actually this is the perfect situation. In dimension 2, there are two possibilities when these successive minima are different. So you get three possibilities, yes? X again, or you may get a curve passing through X, or X, or just these invariants are equal, so then you just go directly from X to the point. And then in dimension 3, you get the surface curve and so on, yes? So, but what we see from these examples is that we have a certain dichotomy. So the case when all these invariants are equal is somehow special. So in other words, it seems that the whole space is special, and this seems to be worth investigating. And then there are other cases when, I mean, the general cases when these invariants are different. And then if the point is very general and you get all these special cycles for it, you expect them to, I mean, they do define a foliation, maybe a fibration, who knows, and one should investigate this further. And then one final remark about this base law of psi is that is the statement which is very important, proved by Ein, Kukle and Lazarsfeld and Nakamai, only characteristic 0, saying that if the point is very general, if it's special, it's not true. And any t, then if you look at any reducible component of this base loci, any section will vanish at a certain effective order against, I mean, at any points of z. Yes. So, so now these are the next two theorems that we proved with Atsushi Ito, saying that if you have in characteristic 0 a proper algebraic variety, a line bundle, then the volume is equivalent to the product of this successive minima. This is the analog of the Minkowski theorem, and it implies actually the Minkowski theorem in the Toric case. And then in particular, you get this inequality. So if L is big, then the volume over the maximal Seshadri constant to the D is bounded above by that ratio. And then again, it's a very interesting question to study when this ratio goes to infinity. And the next statement says that in the Toric case, you can you don't get anything new. So basically, you just get the classical notions of only one over them. So the successive minima are one over the successive minima of the moment of the difference of the moment polytope. The moment polytope is not symmetric, but if you take the difference, it becomes symmetric. Okay, so about proofs, how much time do I have left?
We started a bit later, so I would say like 10-ish minutes.
Okay, yeah, that's more than enough. Okay, thanks. So about proofs, I should just say that Theorem 3, this last statement is just similar to Theorem 1, so there is nothing else to say. Theorem 2 is new. So what we do in Theorem 2, the left-hand side inequality is easy and it holds for at any point. You don't need special points, and it also holds in characteristic in any characteristic. What is hard is the right-hand side, and this is false in special points. One can find Toric examples. And to prove this, we reduce it to another statement, which is stronger. We have an upper bound on the global sections in terms of this Seshadri constant. And this looks a bit strange, but this is what it works. We define this polytope square of epsilon 1 epsilon d just to make things work there. This is an improvement of the method of counting jets of Nakamae. So actually, this is how we got the idea by looking at the paper of Nakamae, and somehow introducing these polytopes makes his argument much powerful. And so we reduce to prove this statement, and then this statement also can be reduced to another statement about the difference for all p. So we can show actually that if you take p enough, because when p is large enough, then this statement h0 of I of x p plus 1 L is 0. So therefore, when you add up the inequalities, you get what you want. So we reduce to this statement, and for this statement we look at jets. So what do? Is we look at the image of the quotient. We take the short exact sequence. I mean, it's not exact. We look at the exact this exact sequence. The space, the third space is just a space of polynomials of degree p in d variables. And what happens is that we pick some I such that it's different from I. I mean, we pick some I such that epsilon I is different from the rest. We pick a component. We take the blow up and we take the proper transform of that blow up, and that proper transform should intersect the exceptional locus. And by that proposition that I just mentioned of Kukle, Lazarsfeld, and Nakamae, the section should vanish along that intersection. So in particular, the image of R is obstructed. I mean, it cannot be everywhere. The image is containing these polynomials which vanish of this order along this intersection. And using this idea, it's enough. It's enough then to find an upper bound on the space of polynomials vanishing of certain order along certain subvarieties. And this is the last statement. We reduce to this statement. So basically, if you have it's not a flag, but you have arbitrarily reducible subvarieties of all codimensions, and you fix numbers and you impose vanishing order along the generic point. And then the statement is that the number of sections attains maximal when this is a linear flag. This is the statement. And the proof is just by cutting with general hyperplane sections. So in particular, and this was one of the ideas how to get this theorem of Minkowski. It's implicit in the work of Nakamaya, this bound. So the volume is at least this 2 epsilon 1 epsilon 2 minus epsilon 2 squared. And the reason we can prove it using the theorem, because you have this explicit formula. You can also compute in dimension 3, for example. Okay, so finally, I would like to mention some questions, some problems. In the Toric case, first of all, can one compute this maximal Seshadri constant? Because we don't compute it actually. We can estimate it up to bounded constant. And is it rational? I'm not sure if it's rational. Also, the same question for the other successive minima at all the points. Can we estimate or compute them? Second question, if we consider all these pairs, X and L, but L may not be line bundle, maybe Q line bundle. That's why I put I put bounded in. Well, so are they bounded if we bound the width? Width is the last. Sorry. This is epsilon 1 of L. So if we bound the width, the maximal width, are these pairs bounded in a certain way? This is also an interesting question. Then some other question is, if we take again non-Toric case, if L is an F of Kodara dimension at least 1, is it true that the kth successive minima, which we know that is strictly positive, is it at least 1? Also, something similar to Ein-Kukle-Lazar's-Feld question, conjecture, is that if the width against all the cycles of the variety is at least 1, does it follow that the Seshadri constant, the maximal Seshadri constant is at least 1? This is also a question inspired by conjecture of Collar, saying that if you have a low canonical model, then you should have this lower bounds for this the first and the last successive minima in terms of this sequence, which is quite well known. And then another question, which would prove rationality if it's true, is first of all, we know that if positive, this ith successive minima are given a supremum of the locus of this ratio P and Q, such that the codimension of this base loci is at least I. And the question is, when is the supremum equal to the maximum? And when is the supremum maximal? If it's true, then you get rationality. So is it true for fun or for adjoint line bundles? Next question is what happens to the algebraic geometry analog of the Minkowski theorem 2? How about characteristic positive? Because we use heavily characteristic 0. I mean, the result of Nakamai and Ein-Kukle-Lazar's-Feld, they use characteristic 0. They differentiate sections. So it would be interesting. It would be interesting to find out. Maybe the statement is true unless something, some strange vibration appears there. I'm not sure. What is the algebraic geometric analog of the transference theorem would be another question. And another question is to study this dichotomy, as I mentioned, when all these are equal or when they're distinct. And they're related to some work of Huang, Keum, and Nakamai. And also, this is some explicit, I mean, something related to the previous question. And I think I mentioned it before, that if the ratio is large enough, then there should be, there should exist some vibration, and this Sashari constant should come from lower dimension. And also, what is the Simion in combinatorics? Is there a geometry of numbers analog? And finally, if you look at this base loci, but at the first place where it's interesting, so just after the Seshadri constant, there are somehow minimal cycles through X. I mean, they're invariant. And the question is, do they really have bounded length? Okay, so these are some questions which appear naturally in this work. Okay, so I'll stop here.